Hi, welcome to the e-lecture on Arduino GPIO programming. Okay, so at the end of this lecture, you will be able to understand the general architecture of a simple microcontroller. At the same time, we will also learn how we are able to read and write to devices using the GPIO pins. Okay, and though we have already been doing all this stuff using sketch programming, the objective is now to introduce you to the actual bare metal or low level programming. Uh, and in order for us to do that, we need to have a good understanding of the microcontroller's internal design and architecture. Okay, so before we get onto that stage, we first need to get familiarized with ones and zeros. In other words, binary numbers. Okay, so in essence, binary is basically the fundamental way in which we represent data in digital systems. Okay, and uh, data is represented as either ones or zeros. Okay, and these are basically what we call logical representations. Okay, in reality, of course, these logical representations uh, are also translated to real world signals in the hardware. Okay, and these are actually voltage signals. Logic 0 is always 0 volts, so there's no confusion in that. But logic 1 depends on the microcontroller's supply voltage. Okay, of course I say microcontroller because this is the uh, device you're dealing with, but in essence, regardless of what device you're dealing with, as long as you're talking about digital logic 1, the actual voltage that it translates to depends on the power supply of the device. Okay, or the power, uh, the way the power is configured for this particular device. Okay, so in the Arduino microcontroller, the logic 1 is 5 volts because we are powering the system with a 5 volt supply. Okay, so it is 5 volts. In some systems, if the power is 3.3 volts, then the logic 1 also translates to 3.3 volts. Okay, so that is something we must bear in mind always. Now, a binary representation, okay, the zeros and ones, we can basically call them a bit. Okay, so it's either 0 or 1, okay, false or true. There are of course other representations. The common one is byte, which is 8 bits, and another common term you will see in most controllers is a word. Okay, and the thing about a word is it is not uh, kind of consistent across all systems. It depends on the architecture of the system you're dealing with. Okay, so for some systems, a word can be 4 bytes, some can be 8 bytes, or some can be even 2 bytes or 1 byte. Okay, so it all depends on the architecture of the system that you're dealing with. Okay, but byte is very standard, is 8 bits. Okay, there's also another terminology called nibble, 4 bits, but that is very rarely used. Okay, so we do not need to worry about that too much. Okay, in terms of representation, n bits can represent up to 2 to the power of n values, correct? So if I have 2 bits, okay, so I have x, x, and y, 2 bits, I have the possible combinations are 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so basically for 2 bits, okay, I have 2 to the power of 2. Okay, so since it's the base 2 number, this is the number of bits that I'm going to use. Okay, similarly, if I have 3 bits, I have 8 possible combinations, 4 bits, 16 combinations, and so on. Okay, if I want to know, or if I want to represent m values, and I want to know how many bits are required, what I can do is I can use this formula called log to the base 2m. Okay, and of course, if the answer, if m is already can be represented directly with a base 2 raised to a power, then you get an integer number. But if not, you may log 2 to the power m may give you a fractional or a decimal value, and then what you do is you take the ceiling of it, okay, in order to know how many bits. So for these two examples here, for example 40 and 100, you cannot represent these numbers directly as just a single uh, number with a base 2. Okay, so when you do a log to 40 or log to 100, you will get a value that is with a decimal point, and then you take the ceiling of it to know how many bits are required. Okay, In general, basically, from the time we learned about numbers, we have been using what is known as a weighted positional system. Okay, so when we first started learning about numbers when we were in kindergarten or nursery, uh, we say we started with number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and then from there it goes on to 10, 11, and so on. Okay, so what we did is we actually were learning a weighted position number system with a base 10, correct? Because if I write 9 alone by itself, we say this is number 9. But if I put 91, then this is actually 9 multiplied by 10, correct? Plus 1 multiplied by 10 to the power of 0. Okay, this was 10 to the power of 1. Okay, so the weight is basically depends on the position, correct? Okay, so that is how we actually represent numbers using the base 10 system, which is basically what we have learned all this while. The binary systems basically have the same principle except they operate on a base 2. Okay, so when I look at this 111001, basically what I do is for this rightmost digit, we call it the least significant bit, LSB. Okay, for this particular bit, the power is always 0. So the LSB always has a power of 0. So to the power of 0 multiplied by 1. Okay, add with. So these are zeros anyway. So multiply by 0, you're not going to get anything. Okay, so this is power 0. This is power 1. Okay, so I'm just writing the powers here: 0, 1, 2. This is 3. This is 4. And this is 5. Okay, so I need to then multiply by 2 to the power of 3 times 1 plus 2 to the power of 4 times 1 plus 2 to the power of 5 plus times 1. Okay, so when I add up all these numbers, I will get this answer here, 57. Okay, so this is basically how your weighted positional number system works for binary digits, and using this I can get the decimal equivalent of a binary number. Okay, hexadecimal is another very popular representation system, which is a base 16 system, and in this you have numbers representing from 0 to 9. So these are the first 10 numbers, and these are the other 6. So the other 6 are represented by the first 6 characters of the alphabet system. Okay, and so basically how we relate the two is, for example, in this example 1E3, 1E3, when I say this is base 16, that means each of these hexadecimal digits can be represented by its 4-bit equivalent. Okay, so 3 is 0, 0, 1, 1. Okay, E is 1, 1, 1, 0, and 1 is 0, 0, 0, 1. Okay, so that gives you the the binary equivalent of this hexadecimal number. Okay, so hex to binary is quite straightforward. For binary to hex, it is the same thing. You group in bits of 4. The important thing is you must start from the least significant bit. You must start from the least significant bit. So for example, in this case, this example here, 111001, this is a binary number. So I need to start grouping them in groups of 4, starting from the least significant bit. Okay, so this is the first group, and this is the second group. So as you can see, the first group has 4 bits, so that directly translates to 9. For the second group, only has 2 bits. So the way you go about this is to just pad zeros until you get a group of 4. So this is 3. Okay, so 3, 9, H is the hexadecimal equivalent of this binary number here. Okay, in terms of representing a binary and hex, different software systems may use different notations or different conventions. Okay, so in textbooks and so on, usually it is quite common to see a base 2 as a subscript, okay, or base 16 for hex. In coding wise, some programming languages put a B at the back for binary or 0B in front. For hexadecimal, some of them put a H at the back or 0H in front. Or another common convention is to put a 0x in front for hexadecimal. Okay, so the convention that you use in a particular programming context depends on the language or the development environment that you are coding in. Okay, so now we're going to look at this bitwise operators. Bitwise operators basically operate on make use of our Boolean operation. So the AND operation, or, and the NOT. Okay, so I will not go into too much detail. Basically, we know how an AND gate, OR gate, or NOT gate operates. Okay, so for example, A and B, the only time when the output is a 1 is when both the inputs are a 1. Okay, then you get the output 1. Okay, for OR, as long as either input is a 1, okay, in this case this 3, the output is a 1 here. And not A is basically the complement of A, correct? So if you look at A, if I do an inverse of A, is this complement of A or not A. Okay, so these are the bitwise operators that you can directly code in C. And why are bitwise operators useful? Because they actually help in this thing called masking. Okay, so what is masking in general? Masking is a way of focusing on particular bits in 8-bit or 16-bit or value, and you only want to sort of change or read certain bits without changing the other bits in that data. Okay, so basically we do two main important things. We either want to clear a particular bit or we want to set a particular bit. If you want to clear a particular bit, what we do is we create a mask where that particular bit is 0 and all the others are 1. If I want to set a bit, I create a mask where that particular bit is 1 and all the others are 0. Okay, and for the clearing operation, what I do is after I create the mask, I do an AND with the actual data. For a set operation, I create the mask and I do an OR with the actual operation. Okay, so let's see how we actually can make use of mask. Okay, and so now we have a variable value, and this is the data inside this variable. This is the binary representation, this is the hexadecimal representation. Okay, now what I want to do is I want to clear bit 3 and I want to set bit 5. Okay, so for numbering wise, we always start as bit 0 is the LSB bit. Okay, that means the one in the rightmost. Okay, so bit 0 here is referring to the rightmost bit, okay, of the data. Now I want to clear bit 3 and I want to set bit 5. That means 0, this is bit 0, this is bit 1, this is bit 2, this is bit 3. So I want to change this particular bit to a 0 and I want to set bit 5. So this is bit 4 and this is bit 5. I want this bit to become a 1. Okay, so that is the objective that I want to fulfill. Now how can I go about it using the masks? Okay, so just remember clear bit 3 and set bit 5. So to clear a bit, okay, let me go back to the slide here. What did we say? We create a mask where that bit is 0 and all others are 1, and then we do an AND operation. Okay, so we create a mask. So if you look at this mask here, only that particular bit is a 0 and all others are 1s. So when 1 ends with 0, the answer is automatically 0. And since I have a 1 for the other bits, doing an AND operation with 1 does not change the original data. Okay, so you can see, for example, here 0 is still 0, 1 is still 1, and so on. Okay, when I do an AND operation with 1s, okay, nothing happens. I retain the original data. Okay, but when I do an AND with a 0, that particular bit becomes 0. Okay, so that is basically how you do the clearing operation. For the setting operation, again the same thing, but now since I want to do a set, okay, what I need to do is I must create the mask such that that particular bit position has a value of 1. And the next thing is the operation is the OR operation. Okay, so this is the OR operation. Previously was the AND operation. So for clearing is the AND, for setting is the OR. Okay, and basically if you look at it, when I do a OR with a 1, the outcome is always a 1. Okay, when I do all with a 0, nothing changes. Okay, the original data is still retained here. Okay, so these are the two important techniques that you need to learn to use effectively when you're dealing with microcontroller programming, because in many cases you want to set or clear only specific bits in the data. Okay, so this is basically how the code will be written. So if you look at this value here, hex F7 is equivalent to, in the binary notation, 11110111. Okay, so when I do an AND with this, so this is my mask. Alright, this is my mask. So when I do an AND with a 0, this bit here, this original data here, whatever is it, will automatically become 0. Okay, similarly over here, the mask is 0 being 00100000. So this is my mask. And now I do, whatever original data I have, I do an OR operation with 1, and the answer will be a 1. Okay, so you have to remember, for clearing, I do the AND operation. For setting, I do the OR operation. Okay, so that is how you sort of fulfill that operation in C programming. Now, let's look at how we're going to apply this to GPIO programming for the Arduino. Okay, so this is the Arduino Uno embedded board schematic. Okay, we have seen this before, okay, in EPP1 and also in the introduction lecture. And basically the main microcontroller is this, which is the AT328P. Okay, so if we just zoom in, we can see that the microcontroller itself, okay, the main things that you really need for a microcontroller to run, as you can see, are just a few pins, okay, which are actually shown here. You need to have a reset pin, okay, the crystal pin for your clocks, the A reference and analog. So these are your analog power supply and reference for your A to D operation, and VCC and ground is basically your main power supply. Okay, so like I said, your Arduino Uno is running on a 5-volt supply over here. Okay, and these pins here, okay, that we normally reference, okay, from as pinouts for our prototyping, we know them generally as pins numbered, okay, from 0 to 13. Okay, 0 to 13. But actually, okay, if you look at how they are mapped back to the controller, they are actually mapped back to 3 different ports in the microcontroller: port B, port C, and port D. Okay, so for each of these ports, we are using the port pins that are connected, okay, to the connector pins, okay, for us to prototype. Okay, so what we are going to do now is, instead of uh, using or referencing them as 0 to 13 like how we did in the sketch programming, we are going to now reference these pins directly based on their port names over here. Okay, either port B, port C, or port D. Okay, again, before we get into that, this is just some additional info on the overall architecture. The specifications again are shown here. Okay, we do not need to go into too many details here, but as long as you can see that we have a lot of peripherals in terms of GPIO, A to D, PWMs, counters, UART, and so on. Okay, so these are some of the things that we will actually be exploring in this EPP2. Okay, and this is the actual pinout of the microcontroller. It's a 28-pin device. Okay, so you can see the pinouts here and how they actually map to the various ports. Okay, and as I mentioned in the introductory lecture, this each pin, okay, except for the power pins, all the other pins, as you can see, they are actually multiplex. Okay, so across different functionalities. Okay, and this is a common thing across all microcontrollers, because you want a controller with a lot of features, but at the same time you do not actually have the luxury of using all the features at the same time. Okay, so you need to make some design choices in your project on how I'm going to use the different pins for the different functionalities that they provide. Okay. This is an important slide, so please always remember this. This shows the mapping of the Arduino pin 0 to 13 to the actual port pins. Okay, so this is important because we are very used to the Arduino pinouts. Okay, and of course we have the convenience factor that these pins are already directly accessible to us through the connectors on the board. Okay, so when you want to now use actual low-level programming or bare metal programming, we need to know how to relate these Arduino pin numbers to the ATMEGA 328 microcontrollers port and associated pin numbers. Okay, so this is quite an important slide which you should have. Okay, so now let's go on to the GPIO programming itself. Okay, so for the GPIO programming, uh, in general, GPIOs are used for a wide range of devices, okay, such as switches, LEDs, digital circuits, etc., and so on. Okay, and for this studio, basically what we're going to be doing is we're going to be first getting familiarized with the GPIO port, and then we're going to do some input output in terms of LED switches and also a very interesting thing which is the 7-segment display, which is the last part of the studio. Okay, this slide shows the internals of a GPIO pin. We do not need to go into the details of how this works, but this sort of tells you that even though you see a single pin, okay, there is actually a lot of circuitry within the processor because uh, as I mentioned earlier, each pin has multiple functionalities associated with it. Okay, so we in our code, okay, we must be able to make sure we configure the pin for the correct use so that it behaves as expected. Okay, so these are the pins. Okay, so you can see here that the three ports that we are using are port B, port C, and port D. Okay, and they are labeled. Okay, and the numbers are all here on this slide. Okay, uh, and interestingly, port D0 and port D1, okay, are also used for the transmit and receive of the UART. Okay, which you will come to again later on. Okay, in another studio. Okay, now let's focus on the GPIO programming part. Okay, so before we use a GPIO pin, the first thing we need to do is to make sure we configure the direction of the pin. Okay, and the direction is set individually. Okay, so for example, DDRB is the direction register for port B. So port B in our case has 8 bits. Okay, and what we can do is we can individually set ones and zeros depending on whether you want it to be input or output. Okay, so this relationship between 1 and 0 and input and output is not fixed across different microcontrollers. Okay, different manufacturers, different devices can have different configurations. Okay, so in this particular device, the ATMEGA 328P, when I set the DDR register bit to a 1, it indicates it's an output. Okay, a 0 means input. Okay, so for the ATMEGA 328 controller, this is how we will program it. Okay, a 1 is output, a 0 is an input. Okay, and once we have configured the DDR register, we can then write to the port register to directly provide the necessary voltage at the pins. Okay, so if bit 3 DDRB was set to a 1, okay, so as you can see, 1 is the output. Okay, so if 1 is the output, once I write a 1 to port B, then port B pin 3 will be asserted high. Okay, so imagine that this microcontroller, this is port B pin 3. Okay, and I configure this to be output, and after that, if I write to port B pin 3 and if I have a LED connected this way, then this LED will light up. This LED will light up. Okay, and as I mentioned just now, the voltage that you see is dependent on the power supply of the controller. So since the Arduino Uno is running on a 5 volts, when I apply a logic 1 to port B pin 3, logically it is 1, but in terms of voltage it is 5 volts. Okay, so you can use an oscilloscope or a multimeter in your lab and you can actually verify that it's 5 volts that you see at the pin. Okay, another interesting thing is writing to a pin, you use the port X. Okay, so when I want to write to a pin, I use the port X register. Okay, X is of course that is generally it's just general term. You replace it with either port B or C or D. Okay, depending on what port you are dealing with. But when I want to read from a pin, I must use the pin X register. Okay, so writing and reading are represented by two separate registers in the device. Okay, so in this case, if I want to read from pin B and I want to read from pin B bit 3, what I do is I read the value and I do a AND with this. Okay, so what does this mask do for me? This mask, when I do with AND, if you remember, when I AND with a 1, only that particular bit's value is retained. Okay, everything else will become 0. Okay, so as you can see, when I do a mask with this particular bit position and this mask, only this value, this bit is set to a 1, only that information is retained. Okay, when I do an AND with a 0, automatically it becomes 0 regardless of the original value. Okay, but when I do with an AND with a 1, then the original data is captured. Okay, and what I can do is by doing this AND operation or masking operation, I will know whether this particular port B pin 3 was having a value of 1 or 0. Okay, so if originally it was 1, after I do the mask, it will also be 1. If originally it was 0, after I do the mask, it will become 0. Okay, so that is how the mask is useful for reading a GPIO pin. Okay, so this is a simple GPIO programming example code here. Okay, where the LED is connected to Arduino pin 13. Okay, so again, how do we relate Arduino pin 13? Okay, so if we go back to that important slide just now, Arduino pin 13 is mapped to port B pin 5. Okay, port B pin 5. So come back here now. So what I need to do is I need to make sure I configure port B, okay, pin 5 as a output. Correct? I need to configure port B pin 5 as an output first, then I'll be able to drive the LED here. Okay, so in this case, this code here is configuring both port B pin 5 as well as port B pin 4. Okay, so in this case I have two LEDs connected. Okay, and what I'm doing here is I'm configuring the port B pin 4 and pin 5, setting the DDR bits both as 1. So both of them will be configured as output. Okay, so you have to draw it here, port B5 and port B4. Okay, now both of them are tied to LEDs with resistors here. Okay, and inside the code here, as you can see, what I'm doing is here I am setting port B pin 5 to 1, okay, and bit 4 to 0, and over here I'm setting port B bit 4 to 1 and bit 5 to 0. So what you will see is you will see that the LEDs are going to be toggling one at a time. Okay, so first the LED over here will be on and this will be off. Okay, and after that this one will become off and this one will become on. Okay, so it will be in a continuous loop. Okay, and so basically this is how you can actually do low level or bare metal programming for controlling the GPIO functionality in the controller, the ATMEGA controller. Okay, this shows a slight variation, and what do you see? The important thing is how we actually represent bit masks. Okay, here instead of writing each time the full binary bit stream, okay, which is tedious and probably prone to errors, what we can do is I can define a pin based on the position of the 1, okay, shifted by the amount. Okay, so what does this do here? When I say hex define pin for 1 shift left by 4, so 1 is basically 0 0 0 0 0 0 0 1, and when I shift left by 4, 1 2 3 4, so what do I get? 0 0 0 1 0 0 0 0. Okay, so in terms of pin number, this is pin 0 1 2 3 and 4. So you see that the 1 is now in bit position 4. Okay, so by using this approach, okay, I can sort of define my masks, okay, based on the actual pin location, and subsequently I can use these definitions in my code, and it's a lot more elegant. As you can see, I can now just set the DDRB using this pin masks, and at the same time I can also toggle the LEDs using this pin mask, and it's a lot more clearer now. Okay, so by just looking at these two lines here, I can know that the first line I'm going to set one of the pins to high, and in the second line I'm going to set another pin to high. Okay, so it becomes quite clear and more readable by using this kind of definitions in your code. Okay, so this is another example where instead of just LED, we are going to have two different things. One is a switch connected to pin 10 and the LED connected to pin 13. So these are again the Arduino pin numbers, pin 10 and pin 13. So pin 13, as we have seen, is port B pin 5, and pin 10 is port B pin 2. Okay, so pin 2 and pin 5. So let's look at that now. So this is your port B pin 2, and this is your port B pin 5. Okay, port B pin 2 and port B pin 5. And what I need to do, I need to do a reading. So I need to do a read from this, and I need to do a write to this. Okay, so whenever the switch is pressed, the LED must turn on. Okay, if I were to look at the voltage that I would observe at pin 10, what do you see? Okay, so as computer engineers, okay, and you have to be very confident in both the hardware and software aspect. So in terms of the hardware, you can see that this pin here is connected to ground. So by default, okay, so if I say this is 0 volt and 5 volt, by default it is ground. But when the switch is closed, what happens? This pin here is pulled up to 5 volts, correct? So whenever I close the switch, it will go up to 5 volts, and it will stay there until I release the switch. Okay, so whenever I close the switch, I will see a positive edge trigger that will bring the voltage at pin 10 up to 5 volts. Okay, so it's important that we understand how the hardware is to be configured, so we can write the correct software that matches the hardware. Okay, so how do I go about doing this? So again, I configure pin 5 and pin 2 here. And what do? I set pin 5 as output and pin 2 as input. Okay, so in this one line of code, what I'm doing is I am saying pin 5 and with the complement of pin 2. So what does that mean? So if I look at pin 2, it is 1 shift left by 2. Okay, so let's see what is happening. So 0 0 0 0 0 0 0 1, a shift left by 2. So it becomes 0 0 0 0 0 1 0 0. Correct? So this is what happens after I shift left by 2. And then what do? I do a complement operation. So everything gets inverted. So 1 1 1 1 0 1 1. Okay? So as you can see, if I do an AND with a 1, nothing happens. When I do an AND with a 0, I clear that particular bit to 0. Correct? So when I clear it to 0, this one is basically making sure that it becomes a input. Correct? And pin 5 is originally set to 1 for the bit 5 position. Correct? So for the pin 5, it is 0 0 0 0 1 0 0. Correct. So this is the bit 5 position, and 1 and with a 1 over here, which means the output is going to be a 1. Okay, so this is again, I'm combining two different uh, uh, operations together. Correct. I'm setting the output as well as the input together in one line. If you think that this uh, is prone to error, you may make some mistakes and so on. What you can do is you can do it separately, line after line. Okay, as long as you understand what you're doing in terms of using the mask. Okay, and subsequently I'm going to check on pin 2. Correct. So I do an AND with pin 2. So I do an AND with pin 2. I'm going to AND with this particular mask here. Okay, so I'm only going to look at what is the value of pin 2. So if pin 2 is high, so in this case, this output is a 1 if the switch is closed. Okay, so if that is the case, then I will set the LED port pin 5 so that the LED is switched on. If not, I will switch off the LED. So I'll put a 0 to port B pin 5. Okay, so this is 1 to on the LED, and this is 0 to off the LED. Okay, so this set of slides, as we have seen, basically what it has done is given you a introduction into some basic programming techniques that you can use for GPIOs in general. These masking techniques and so on, of course, general techniques which you can apply to even other studios. Okay, because as long as you know that in a register I want to set certain bits or clear certain bits, you can use these masking techniques, and if you use it correctly, it can make your code a lot more elegant and readable. Okay, even for yourself in the future. Okay, so that is the objective of the this e-lecture here. Okay, so I hope that with this you are well equipped to handle the studio. It's a good studio where you will learn to do the hardware stuff, okay, in terms of switches and LEDs, and you figure out how to do the correct masking and correct programming techniques. And of course, at the end, you also have a nice opportunity to play with the 7-segment display as well. Okay, so that's about it for this e-lecture. I'll see you all in class for the studio. Thank you.